You will find that as the tutorial session progresses, the question becomes more of like, you know, the first two tutorial was really a lot of math, very abstract, basically thermodynamic physics. Okay, so now we are actually going to apply a lot of what we are doing. So I think the most difficult part is over. I think so. Okay. Right, let's try question number 1. So for a system that does work, reversibly, and given that H is the enthalpy, given that H is equals to UV at U plus PV, derive the relationship dH equals to TdS plus VdP. Okay, you may be asked to derive such thing during the final exam. And subsequently, show that well, this relationship holds. And subsequently, obviously means that you need to use the first part that you have derived. Okay? Now, I think the first part is relatively straightforward after all the weeks of doing partial differential. So, now, since we are given H is equals to UP, it makes sense to start with dH. Because someone wrote an email, asked me, you know, how do we start giving any equation? Obviously, usually there's some hint. Like, we are given H is equals to U plus VV, so show that dH is equals to TdS plus VdP. Obviously, the logical way to start will be to start to differentiate to get dH, right? So therefore, now by now, we should be very familiar, I hope. dH is equals to du plus pdv plus vdp. But then from the first law of thermodynamics, du for a system that does work, du is equals to dq minus pdv. And from the second law of thermodynamics, we know that ds is equals to dq over t. Or dq is equals to, correct, ds is equals to dq over t. Or dq is equals to tds. Right? So tds substitute into here. So du is equal to tds minus pdv. And then if we substitute du into this term here, what we get, of course, is dH equals to TdS plus VdP. Okay? Now, the next part is subsequently show that this relationship holds. Now, the clue in trying to minimize the time is that when you see a relationship like that, okay, you have dH, ds, and dP. What you do is let H be a function of S and P. I did not choose this arbitrarily, okay? Because looking at this equation, there's dH here, ds, and dP. So the first thing that comes in your mind must be let H be a function of S and P. And you'll find that the rest will be, everything goes into place. So let H be a function of S and P. Then of course we know that dH is equals to dH by ds at constant P multiplied by ds plus dH by dP a constant S multiplied by dP. So now if you equate equation 1 and 2, right? 1 is this one here, or this one here. So you can see that dH is equal to TdS plus VdP. So therefore this term here must be equals to T, right? Purely by inspection. And this term here is equals to V. Okay? So now we have these two relationships. Now, the first one is a couple of you still have not got this yet, so let's try to do this, okay? For the rest of you, I'm sure you've got it, so please bear with it. Now, dh by ds is constant p equals to d. So now if I differentiate this term with respect to p a constant s, so what I get is differentiating this term with respect to p with constant s, I get d2h dp ds. And that is the same as dt by dp at constant s. dt by dp at constant s. Similarly, now this one I differentiate by dp, right? So now I differentiate one more time with respect to s at constant p. I will get the same thing. So these two terms are exactly the same. And if these two terms are same, so therefore these two terms must be the same. Okay, because you see when you, in partial differential, you have two variables s and p. You can differentiate s and keep p constant first, and then after that differentiate with p and keep s constant. Or you can do it the other way. Okay, both are the same. So first you differentiate with s at constant p, then you differentiate at p under constant s. It doesn't matter which step you go first, the final result is still the same. Okay, as a result, that is why these two terms are equal. Okay, this two terms is exactly what I'll type out here. And if these two terms are equal, so therefore dt by dp at constant s must be equals to dv by ds at constant p. And basically that's what we're proving. Okay, the only thing you can save a bit of time is when you're asked to do something like that, dh is equal to ds plus v dt, the first step you should do is let h be a function of s and p. Okay, similarly, if you get other thing, well, just dg, ds, and dp. So h is a function of s and p, and then the rest will just fit into place. Are we all clear? Right. We can come back to that later. I think we have quite a bit of time today. Right, let's go on to the next question. Now, using the appropriate Maxwell relationship, show that for any moles of an ideal gas, ds by dp at constant T equals to minus nR over P. Now, again, someone asked me how do I start, which Maxwell equation should I use? Because there are four Maxwell relationships, right? Now, obviously, if you're asked to prove that ds by dp constant T equals to this term here, you will look for the Maxwell relationship that has ds by dp a constant T. And obviously, there is one here because from the Maxwell relationship, dg equals to minus s dt by v dp. Now, in exam, this relationship will be given, but the next one may not be given, but you must be able to figure it out. Okay, so I go through it. Now remember in lectures, if we have this relationship, and if all of them are state function, how do we get the next step? We do not need to prove, okay, we can just put Maxwell relationship minus ds by dp at constant T is equals to dv by dt at constant P. Okay? If you can do this, then you should be able to do any of all the other Maxwell relationship. And that is the system here. ds, okay, ds by dp, so dp on the other side, at constant T, of course it's a minus here, is equals to dv by dt at constant P. Okay, now, some of you have read other literature, and the literature says that ds by dt at constant t equals to minus dv by dt at constant p. Now, that is the same thing. The minus can be on either side. It is the same thing. Okay, so there is no inconsistency. If this minus sign is on this side, it's exactly the same thing because you can just move the two terms across, that's all. Okay? Right, now that we have got this term here, and we are asked to prove ds by dp at constant t equals to minus nr over p. Now, the next step is, obviously we need to use the information on the ideal gas. Because it says, prove this relationship is true for an ideal gas. Okay, now, an ideal gas is a gas that has the individual molecules has got no interaction with the neighboring molecules. Okay, that is the definition of an ideal gas. But for real gases, in most part, we can approximate them as ideal gas, except during the point when you compress, where, you know, when you compress a gas, right? Let's say you compress the normal atmosphere. Now, at some point when the pressure is too high, some of the gases start to condense. Okay? So, at the point of condensation where there's discontinuity, then of course they are not ideal gas. But within the pressure range whereby there is no condensation, we can always approximate them as an ideal gas. Okay? And in theory, the higher the temperature, the more ideal is the gas. Because the higher the temperature, the further are the atoms or molecules apart. So basically, that's all we need to know. So when we are dealing with gases, unless they condense, other than that, within certain temperature range, it is very safe to assume them to be ideal gas. Okay? So coming back, so we know that in the ideal gas, PV equals to nRT. Or now, right now, I will expect you to be familiar with the partial differential. You really need to. Okay? And I think it's within all of you to do it. Okay? So, how do we do now? P is a variable, V is a variable, N of course is a constant, because N number of moles, R is a gas constant, and T is a variable. So when in partial differential, what we do is we differentiate all the variable terms. And if we have two terms like PV, we keep one constant and differentiate one. Then we keep the other constant and differentiate the first one. So basically that's what I've done. P dV plus V dP. So I keep P constant, dV, then keep V constant, dP. That is the standard way of doing partial differential. Okay, even if you have three together, you just differentiate one and keep the other two constant, and then, you know, do step by step and so on. So P dV plus V dP is equals to nR dt. Okay? Because we don't differentiate N and R because they are constant. Then, but at constant P, now why do I choose a constant P here? Because of this relationship here. Now we are asked to prove that ds by dP at constant T is equals to this. So therefore, and from the Maxwell relationship, this term is equals to this term. Now this right-hand side term has got a constant P condition. So therefore, I need to obtain this term. In fact, I need to prove that this term is equals to nR over P. So that's why I invoke the constant P. Okay, the steps are all very logical, they're not random. So you just need to follow. So we know that from the Maxwell relationship, we have this equation here. And therefore, on the right-hand side, or rather I'm asked to prove that ds by dp at constant t is equals to this term. Now when I look at the right-hand side term, I see a constant p. So therefore, it makes sense now for me to convert this into constant p. And you can more or less see the form that is coming up, because this is dv by dt. You got a dv here and you got a dt here, right? So there is a logical reason why I remove constant p. So at constant p, we can remove this term. So now p dv equals to nr dt. So if I move the dt over, so dv by dt, now we know that this equation is only true at constant p, because I have invoked the constant p to remove this term here. Are we good? Right. So now, well, bring the t over dv by dt, dv by dt at constant p now is equals to nr, so remove the p over, so nr over p. So therefore, we now know that this term is equals to nr over p. So therefore, ds by dp is equals to minus dv by dt at constant p, and that gives us minus nr over p. Okay, are we all? You may be asked to derive a simple relationship like that. So just remember the steps that I did. Okay, the first part is H is equals to U plus PV, where I'm asked to prove this. So it makes sense for me, for the first step, I should start with DH. So therefore, DH is equals to U plus PdV plus VdP. And then I work my way from there. Question I usually set such that, if you move logically, you will reach the direction you want to be. Right, then the next part is subsequently show that from this relationship, you get this. Okay, so therefore it makes sense that, in fact, from Maxwell relationship, we already know that dt by dp at constant s is equals to dv by ds at constant p. But now we ask to show it. So it makes sense to start by saying that let h be a function of s and p. Okay, you do not go into any other variable because you have an s here and a p here. So because you know that when you differentiate h, you will get ds and dp. So let h be a function of s and p. So when you differentiate dh, you find that you have the ds and dp. Then you can now compare this relationship with this one here, and of course you derive what is t and what is v, and then you differentiate further, you get what is required. Okay? For question number 2, you're asked to use an appropriate Maxwell relationship to prove this one. So therefore, all you need to do is to look through the Maxwell relationship. One of them will definitely give you ds by dp. Because if this term doesn't exist in the Maxwell relationship, there's no way I can even do it. Okay? So if you look through Maxwell relationship, you find this. So now we're talking about n moles of ideal gas. So therefore, we must try to find what is this term for ideal gas. But we already know PV equals to nRT, and we know this is the constant P. So therefore, I invoke the constant P condition. Are we good? Yeah, if you need to talk among yourself for a few minutes, it's all right, fine, yeah.
Then the constant y and x doesn't don't care. Oh, the bracket because we also multiply the x, y, and the other y, x.
Oh, because when they multiply, they are the same.
Oh, really?
No, as in, this one is what? This one is because they multiply, it's the same one.
The same value.
Yeah. Yeah, there is no fucking logic explanation one. This whole fucking thing is a mess.
So
You just multiply, because your below will be x, y. If you realize you want. It's just like that. There's no
Now, I mentioned
hard reason about it.
there are four such relationships, right? dg is equals to minus s dt, and there are three other. It will be given, yeah. But the second part will not be given, but you are expected to be able to just derive this one directly from what is given. Okay? So if I ask you, look for the appropriate Maxwell relationship, so you need to look for ds by dt. So from the four equations, you should be able to find one that fits what you require. Right, let's move on to the next question.
The way they teach, they don't teach you how to do it. They
Now in this
teach you
question,
what to do.
you have a piece of copper.
Tell what to do, like you don't know how you need to do it.
So pressure is being
I don't give a fuck what to do. I know what to do.
exerted
How is it done?
to compress the piece of
I mean, in the net also, they don't teach you how. They just teach you what to do.
Shall we start?
Uni, bro.
Okay, we can continue discussing after this, so that everyone know we don't get distracted. That's all. Now, if you have a piece of copper that is compressed, it says calculate the change in specific entropy of copper when the pressure increased from 1 atmosphere to 10 atmosphere. And you're given what is 1 atmosphere. You're given the atomic weight for copper, and you're given the density for copper. Okay? Now, we know, calculate change in entropy. Now, when you're asked to calculate the change in entropy, right, what does that mean? What are you looking for in a Maxwell relationship? If you're asked to calculate change in entropy, it means ds, isn't it? Because change in entropy is equals to ds. Similarly, if you're asked to calculate change in temperature, then you look for dT. Or you're asked to calculate change in pressure, then you look for dP, because these are change in entropy, change in temperature, and change in pressure. In fact, the equation, the question has given you all the information. It says that you have been given this relationship, and you can see that there is a ds here. In fact, you must familiarize yourself. This is giving you ds by vp, So it has given you ds by dp under constant t. So straight away you know that ds is equal to something dP already. And the question is asking, if you increase the pressure, what is the change in entropy? And this is exactly what you need, right? To calculate delta S, you must integrate this term with respect to dP. So the question is put in such a way that it's already giving you, helping you to solve your problem already. So we are asked to calculate entropy change when the pressure change. That means the rate of change of entropy with respect to pressure. So we are actually, the question is giving you this. Now the question gives you the Maxwell relationship. The question went on even to give you the definition of the volumetric thermal expansion. The volumetric thermal expansion is basically, excuse me, if you have a piece of material, and if you were to heat up the material, it will expand, it changed by a certain volume. So the delta, the change in volume divided by the original volume is what we call the volumetric thermal expansion. Just like linear expansion, okay? And it's already given you that the volumetric thermal expansion is defined as 1 over V dV by dt constant P. Now when you look at this and you look at the other equation, it's basically giving you a lot of hint already. Okay? So now the question says, if I were to increase the pressure onto the piece of copper, what will be the change in entropy? And straight away, we must be thinking of this part here. Straight away, we must think, whenever you're asked to calculate change in entropy, with respect to change in pressure, you must be thinking of delta S equals to integral of something dP. Okay? And now, let's try to do it now. So we're given this relationship. So the change in entropy, S2 minus S1, that means S1 is when the pressure was 1 atmosphere, S2 is when the pressure is 10 atmosphere. So therefore it's integral of ds from 1 to 2. So that is equals to, now because ds by dp at constant t equals to minus, so you need to put the minus here. Integration from P1 to P2 dv by dt at constant p. But we know that dv by dt at constant p is equals to alpha multiplied by the molar volume. Right? So if I move this term over, so we know exactly what is dv by dt. So we know that dv by dt at constant p is equals to the molar volume multiplied by the volumetric thermal expansion. So now for a piece of solid, we can safely assume that the volume is constant. Because when you squeeze a piece of solid, right, it may deform, it may shorten, but the volume is always constant. When you press a piece of metal, you know, it will go shorter, but it will expand the other way. Similarly, the volumetric thermal expansion is constant. Now, this is not true if you're talking about gas. If you are compressing a gas, the molar volume is not constant, okay? Because gas can be compressed by a big amount, but not solid. And so now we substitute this term in, and when you these two are constant now, So when you integrate a constant with respect to dP, it's basically this one multiplied by the change in pressure. So S2 minus S1 is equals to minus this term here multiplied by the molar volume and the change in pressure. So the pressure is from 1 atmosphere to 10, right? So integration will be 10 minus 1 will give you 9. And you key in all the other figures, you should be able to get the answer. Okay, I think what I want to emphasize on is the different steps that you go through. You need to be familiar with maths, but I think after the last 3-4 weeks of going through all this, I trust that, you know, it may take you a little bit slow, but fine, I trust that you really have to do it like that. Are we okay? Are we good at that? If I tell you I spend a few minutes and talk on my notes, sorry, talk on myself, and then we move on.
I just certain formula actually.
And if you have any
Certain
questions,
formula
please feel free
can
to
write.
ask.
Don't need to
Yes.
understand.
No, because for me, you know the time we do the integration.
Yes.
Then you can.
The volumetric
How come you can?
uh,
Cannot.
coefficient of expansion, sorry, the molar volume is constant, the volumetric is constant as
Don't
well.
have, then become like that.
I mean, there is some change, but
That's
for
what I understand.
practical engineering,
I can't remember we
it's almost
the white
negligible.
camera. Then you tell me.
Because when you hit out a piece of metal, you expand, but
The T-square.
the expansion is so small that it's negligible.
Now don't have P.
But if you are working on a gas, you cannot take this as constant, okay? You have to convert all this as
Isn't
a
that time you
function of P.
integrate?
But for solid, it's
Times
very
in
easy.
the T, ma.
No, the T is given already.
Well, if it's gas, you know P,
So
right?
you need to.
In the case of
Then
gas,
300 will put here, ma. Then
now you can only assume that
Then you get.
it is
Then minus.
an
Then
ideal gas.
yeah, so you
So we know that PV equals to RT, right? And so therefore V equals to RT
Same one,
over
bro.
P.
You can just if we do
In this case, of course, we assume that we
don't
are
have P.
compressing at constant
put
temperature,
the P.
so we can
Leave
keep
it
the
like this
temperature
because
as constant as well.
it become like alpha V times V
Yes, for gas you have to substitute
minus
that term
alpha
at the
V
end
times
onto
V
the P.
P1. Then you put it.
But for solid, usually it's very easy.
Same.
Fortunately, as materials engineer, most of the time we deal with solids.
So I will just plug in this formula.
Okay.
I mean the lecture got this. So I just put.
Oh, the lecture got this.
Yeah, got this formula. Then I just put in.
You see, this one I saw in the lecture. He got say this
Yeah.
BDD.
Then I just put in this one. I mean like this short.
Or you do at home.
No, just now I do.
Oh.
Starbucks is nice.
And share. Only buy for yourself.
I can mark. Don't know how many.
Then you need to buy for vanity. You want to pass it.
Are we on good?
Big cup. Now you know what? You cannot buy it talk. So you must buy with stuff.
Okay, we are doing the one on gas, not exactly what you just asked. Right, let's move on to the next question. And, you know, if you're not sure, we can go back to it. Good. Right, question number 4. The volume coefficient of expansion. Again, alpha V is given. And the isothermal compressibility. The word isothermal means constant. When you are compressing something under constant temperature. Okay, that's what it means. So the expression for the volumetric thermal expansion is given, and the isothermal compression of a system. Now, both of this expression is valid for solid or liquid or gas. It's just that solid and liquid and gas behave differently, but the expression is valid.
1 over V.
Now, the question now is, derive this term here for an KT for an ideal gas.
I got it.
Okay, now, how do we start? Again, someone asked me. Let's do alpha V. How do we start? Now, again, we look for the appropriate Maxwell relationship, isn't it? We know by now that there is one Maxwell relationship that has this term here. Right? So, so for an ideal gas, PV is equal to RT, and so therefore expanding, again, using partial differential, because now we're using partial differential all the time, because in thermodynamics there are many variables. If it's just one variable, then we can just do a simple differentiation. So P dV plus V dV equals to RT. Now, we are asking to derive this term at constant T. Everything okay there? Okay. So, now at constant P, we can remove this term. So P dV equals R dt, and now we know that we can move the dt over. So dV by dt now is constant P because this relationship is only true for constant P. Because in this relationship we have invoked the condition of constant P. So we get R over P, and now of course if we multiply 1 over the molar volume on both sides, we get this term here. Now, but then of course the molar volume is equals to RT over P in the case of gas. Okay, in the case of solid, we actually don't have to move further. So now we just substitute this term for this, and you'll find that the volumetric thermal expansion for an ideal gas is equals to, which is this term here, is equals to 1 over T. Because, well, basically everything just cancels out. I have posted all the solution. But it's all right, you want to go through step by step, it's fine. Yes.
You can let him know. What he
Sorry?
did so long. You just go out and take a pencil.
Because the V can cancel.
My solution is
I'm
different.
serious now, you see. 1 over V, if you multiply V over T, the V you cancel 1 over T at constant P.
Oh,
1 over P at constant P.
but if you use a desktop,
Answer
you
here.
should be able to.
I'm correct.
Oh.
Yeah, they want to do this.
Sorry about that.
Oh,
So are we okay with this step? The next step is we want to find the expression for the isothermal compressibility. And the isothermal compressibility is defined as the rate of change of the volume with respect to pressure, meaning that when you apply pressure at constant temperature, basically that is what isothermal compression means. Okay, so the other thing I hope you realize that whenever you see a differential of this form, let's say if you try to put some physical meaning on the equation, it's easier to understand. Let's say if you put dy by dx at constant z, for example, what it means is that it's not just dy by dx as constant z. It means the rate of change of y with respect to x. That means how y changes when you change x under a constant C condition. Okay, so when you see something like that, it means that how the volume change when the pressure change under a constant T condition. When you try to look at it this way, I think it's more meaningful and it helps you to understand the physical characteristic much better. Otherwise, it's a very abstract dV by dP is constant T. Okay, so because we are dealing with real materials now, we apply all these physics onto real materials. In the next few lectures, you see more and more of this. Because the first part, they're mini maths, dy by dx. Although you know the operation, but you will learn to appreciate all this when you can visualize what this one means. That means dV by dP, meaning that when you compress something, change the pressure, how does the volume change? And in this case, we keep the temperature constant. Okay? So let's do that then. Now again, we know that, well, let's start with the ideal gas again. Now PV equals to nRT, PdV plus VdV is to RdT. Now, what do we want now? We want a constant temperature now. So, it's natural for us to invoke at constant temperature, these terms become 0. So therefore, PdV minus VdP, moving one of the terms to the right hand side, PdV minus VdP are equals to minus VdP. Then again, move the P over the other side. You see the question has already set us up for these logical steps. Because it's asking us to find dV by dP. So now we get dV by dP equals to minus V over V, and therefore we move the V, the molar volume, to the left hand side, and this is the definition of the constant pressure, constant temperature, compressibility. Okay, so therefore that is equals to 1 over V.
Like what you feel from the question straight away.
Okay, split a few minutes and talk. You need to clear this out. Then move on much more.
So how to show this is this one? If you devote it T dP, yeah, because T dP and constant pressure is V
Maxwell.
yeah, V over dS. V over dS is a constant T because the rainbow one, remember?
Yeah.
I show it. Then why he do so long?
No, this one is because the first tutorial one. Like for those who doesn't
Then
understand.
this one, he asked you to show what? Is the ideal gas. What is supposed to show?
NRV or negative.
Or it must be shown in the number of moles. PV plus nRT. nR is the number of moles.
It's just like you put the T here, then become.
You put the T over the V, then the nR over the P, the rainbow. Bro, what you need to study, bro? Bro, the next up Einstein.
You're not used.
Really? Serious?
It's all right, don't worry, you need to discuss. But by now you're all comfortable with partial differential, right?
Because I see question 4 or 5.
next you need
This
to
is
know
quite easy. Then asking him is it I don't know why is it
yes.
so easy?
The derivative the molar portion.
And he never tell me tell the prof. You like you teach him the wrong bro. I show you how you answer.
Common closure theorem. Then you just take this one from here, you can split. Then do integration, you get the integration.
I have to
Right?
understand.
From here to here. This line to this line you can see then you sub 1 into 2 or sub 2 into 1. Done. But I don't know what's the solution.
Oh, this is different. This is just move.
Just remember ds equals
This one is not.
delta squared.
This one is just dividing one by one.
I thought you haven't started.
But the thing is, I don't understand the part. I'm just doing that.
Yes, don't skip lah bro.
No idea what's
He's still
Right,
gonna take
I need to start.
just take one.
I think we do have enough time
I
for
mean,
this question.
for me I taking when I
Shall we
do the
start?
holiday.
Oh, holiday lah.
The recess.
Okay, you can stay back and discuss. Let's see, and then we'll come back. It's already totally fine. It's good to discuss together. Now, question number 5 say, show that the heat absorbed, which is dq by a system, when its pressure is increased from P to dt isothermally. Now, this question is very interesting. It says that if I have a piece of material, if I were to compress this piece of material, show that the heat absorbed by this system is equal to this term in an isothermal condition. Meaning that when you are compressing a piece of material, right, we are compressing isothermal condition, meaning that the temperature of the material maintain a constant temperature. And in order to do so, we have to either absorb heat or give out heat. Because when you compress something to maintain the same temperature, the material has to give out heat or absorb heat. And the question shows that the heat absorbed or given out is given by this relationship. Now again, we need a Maxwell relationship, but how do we start? Now, because we are asked to prove that dq is equals to something, right? Now, where is dq in any of the Maxwell relationship? We know that there's no dq, but there is a ds. And we know that ds is equals to dq over t. Sorry, dq over t. The other thing is that we also ask, how does the heat absorbed affected by the change in pressure? That is a dp there. Oh, sorry. That is a dp in the equation. So now you need to look for something which is ds by dp. Right? So it saves you some time. Of course, you can do trial and error using there's only 4 Maxwell relationship. But you see, it saves you some time if you know straight away what is the relationship. Now, in this case, the question is very kind. He has given you, this is the Maxwell relationship to use. And at the same time, we know that there is a rate of change of heat with respect to the change in pressure. So we're looking for dq by dp, but we know that there's no dq, but there's a ds. whenever you see the Q, it is always associated with the ds. Because second law say that ds is equals to dq over t. Okay? So every time you see that, straight away, it should ring in your mind. Now, so a test piece of copper under load in a tensile machine meaning that it is being pulled, so that's why I put the dp here. A test piece of copper under load in a tensile is stretched by a small certain increase, assuming the tension and contraction remain elastic, meaning that it's not pulled beyond the thing deformed permanently, right? As long as it's elastic. Does the temperature of the copper increase, decrease, or remain constant? So what it's saying is that show that this is the heat absorbed, show that when you pull, right, does the temperature of the copper increase, decrease, or remain constant? Now, but now we are doing an isothermal condition, meaning that temperature is constant. Okay, so we try to answer the question, say, by assuming that does the temperature of the copper increase, decrease, or remain constant? So let's look at it, okay? We start by this relationship, and of course, what is dV by dt? Well, it doesn't matter because we already know that 1 over V dV by dt is equals to alpha. We can already see, we can already visualize this term is going to be something similar. Okay, so now minus ds by dp at constant t equals to this. So ds at constant t, we move the dp over, or ds, now we know that 1 over v dv by dt is equals to alpha, so therefore this term is alpha v. If you remember the previous question, right? dv by dt at constant v is equals to, you can move this molar volume over, so it's going to be alpha. Now in this case, we are not working on the molar form, it's perfectly fine. Okay? So now, so this is equals to alpha v dp, where alpha v equals to 1 over v dv by dt. Now, for a reversible process, we know that ds is equals to dq over t. So therefore, we substitute this term here, we get dq over t is equals to this term, and then we move the t over, and that is what we are asked to derive. Now the question gives us one information. Note that dp is negative. Now if you do not know that, that's fine, because the question is given you. Okay, in exam things like that will be given, because it's just the standard way intention is treated as negative. So dp is a negative number. Okay, so now we have proven this term here. Now, if you look at this, if you look at the heat absorbed, okay, it's equals to minus. Now the temperature cannot be a negative value. Okay, the volumetric thermal expansion for copper we know is not negative. Negative means when you heat up copper, it contracts, it doesn't expand. Okay, the volume of a material, of course, cannot be negative because it is a physically, it's a physical material. Okay, now dp is negative. So therefore, this whole term is actually positive. Okay, now the whole term is positive means what? It means that If dq is positive, it means that the system is absorbing heat. Okay? The system is absorbing heat in order to maintain a constant temperature, because the whole process was done in isothermal condition. So what it means is that the copper must be cooling when it is stretched, isn't it? Can you try to understand? Now, when you put a piece of copper under isothermal condition, that means you're pulling a copper such that the temperature remains constant. But then our derivation shows that the copper is actually absorbing heat because dq is positive. So the only way we can account for it is the copper must be cooling. When you stretch a piece of copper, it is cooling. Okay, and because it is cooling, it is absorbing heat in order to maintain a constant temperature. Okay, now if you were to stretch the piece of copper in a reversible condition, you will never notice any temperature change. Because the copper is cooling as it's stretching, it is also absorbing heat at the same time to maintain a constant temperature. But if you stretch it suddenly, it takes time for the copper to absorb heat, so therefore you can feel that it's cold. Okay? So basically that is the answer here. The proving part is relatively simple. Prove that it is equals to that. Okay? But what is important about this question is that it shows that when you stretch a piece of copper under isothermal condition, it is actually absorbing heat. How can the temperature of a copper remain constant if it is absorbing heat? The only reason is because the copper must be cooling when you are stretching the piece of copper. Okay? Not okay. Okay. Now, if I prove something, right, the derivation tells me that this is absorbing heat. But then when I feel the temperature remains constant, how can a material absorb heat with its temperature remaining constant? Not possible, right? If something absorbs heat, the temperature has to increase. But in this case, the temperature remains constant. But we know from this derivation, that it is absorbing heat. So the only way the temperature can remain constant is when you are cooling, the material is absorbing heat from the surrounding to maintain a constant temperature. Because we know that one we cannot disprove. We have proven that it is absorbing heat. We also know that this is an isothermal condition because of this equation. So, you know when you apply heat to something, how can the temperature of that thing remain constant? It can only be constant if that thing is absorbing heat. Okay? So that is the logic behind it. You can actually try out. Well, it's a bit difficult to pull rubber. It's a bit difficult to pull copper because it needs strong force. But if you have the device to do it, jerk something very fast, it will feel good. Okay, it's very similar to, when you have a balloon, right? You suddenly release the balloon, the pressure drops, then you feel cold. Okay, this is very, very simple. Right, I think I have only one more part, so if you need to discuss among yourself. You have only one more question. Question number 7 is shows the relationship between the adiabatic compressibility and isothermal compressibility. Now, I think the day lecture, I said something wrong when I review back. Now, isothermal means constant temperature. Adiabatic is not constant temperature. Adiabatic means more like constant entropy. It is absorbing heat. Okay, no, sorry. Adiabatic means no heat is absorbed and no heat. Okay, so the temperature is not constant, whereas isothermal is constant temperature. Anyway, optional, question 7 asks you to prove the relationship between adiabatic condition, which is constant entropy, with isothermal compressibility. Okay, you're given all this information. You will not encounter this kind of problem, or at least as difficult problem as difficult as this. But the solution is in the textbook. Okay, so I just got one more question to go through, and that's question number 6. Shall we do, and then we still have half an hour to discuss. Now, experiments show that when rubber is stretched rapidly, the temperature rises. You can try that if you take a piece of elastic rubber. If you suddenly stretch it very fast, it feels warm. Okay? The question shows that this implies a negative coefficient of expansion for rubber. Now, most material, when you heat it up, it expands. So you have a positive coefficient of expansion. But in this case, it asks you to show that rubber has a negative coefficient of expansion, meaning that rubber actually contracts when it's heated up. Now, this is true in some of the polymers, because polymers are normally amorphous. If you were to heat up a piece of polymer, they tend to crystallize, and when they crystallize, the volume is reduced. Okay, so you find that the question asks us to prove from this equation that rubber actually contracts when it's heated. Okay, now the reasoning is very similar to the previous question. Now, dq is equals to this term here. Okay, now this is negative, and this is negative. So therefore this term here, if alpha is positive, if the volume is positive, then the system should absorb heat because it is positive. But when you stretch rubber, it feels hot. When the rubber feels hot, what does it mean? When rubber feels hot, when you stretch rubber, it feels hot. What it means is that it's giving out heat, isn't it? If it's giving out heat, this whole term must be negative. Okay? But because dP is negative, T is positive, V cannot be negative, T cannot be negative because the lowest temperature is 0 K. So therefore, the only way for the rubber to absorb heat is because the volumetric thermal expansion is negative. Because, I say when you touch something, if this something feels hot, what does that mean? This thing is giving out heat, that's why it feels hot. If you touch something, it feels cold, it means it's absorbing heat. Okay? So when you stretch rubber is giving out heat. If rubber is giving out heat, that means this whole term has to be negative. Now if this whole term is negative, dP is negative, there's a negative sign here. So one of these three terms has to be negative. Temperature cannot be negative, the volume cannot be negative, so therefore, the only possibility is that rubber contracts when it is heated up. Okay, I think I've gone through all the questions. We still have half an hour. Well, feel free to stay there and discuss or comment if you have any questions. Right, if not, you need to go, feel free to do so. Oh.
The copper you do, you say,
Yeah.
cooling. See, copper might be cooling. Then this one copper
Question 6.
expansion ma. Then how the rubber, when rubber becomes hot,
Because of this situation. Because we have equated to be equals to that, you see. If we don't equate it equals to that, then it's not so. Because we have used this expression. And then in our derivation, we have maintained this equation. And this equation shows that it is
Model 1 is not Model 4. Big 5 is Model 2.
If it doesn't give you that,
Big 1 is part of it. We just found it.
Oh, it's half of it.
Was it? I think you need to download the book or something.
What thing?
You need to download or something. Then this is one module. Part 1, part 2. So this is another module. Yeah, this one.
And below. Yeah. Okay. So I've got all my materials. Yeah, ask about the question.
So this formula, I will do question 6.
I don't understand somewhere. I got to talk like that. No.
So this question, this formula is inside the
Yes.
it's inside the clear one, right? This is under the Gibbs one, is it?
I don't know. No, the very short one. The tutorial lecture 3. I don't know. Why? You wanna ask us? You want to ask? Is it?
I don't know how to ask.
Oh, if ask, I will just ask if you want me to ask. Because I'm still trying to visualize. Because over here they say rubber is stretched rapidly, then Q is negative. Q negative means it through, it emit out the heat. But this one also the same. Is stretched by sudden increase. Sudden increase means also the same. But for this case, Q is positive instead of negative. Means it absorbs the heat. I mean, so I confused.
Oh god.
I need to do my report. I haven't finished my hormone report.
The light really over so long already.
No, for my one hormone report is.
Hey bro, you understand or the last two questions?
I mean, need to submit this. Oh, last
This one is the copper one.
Yeah, it's stretching.
Stretching Q positive. Right?
Okay, what you know is the alpha is positive, right? And you know dp is negative, right? So this whole term has to be positive, right?
Okay, yeah.
Means delta Q is positive, means it gains heat, right?
Really?
Yeah, it's absorbing heat.
Okay.
So for isothermal condition means it needs to lose heat for it to maintain same temperature.
Yeah. Okay, so but how come in this case it behave the other way around? Like you also do the same experiment or you also
Because in
put-
this case the alpha is negative. He said it ma. So you know the dp is negative. You know T is positive, D is positive, so this one has to be negative because we know this one is negative.
Oh.
Yeah, we know this one is negative because it says temperature rises, right? So when temperature rises, yeah, that's why dq is negative. To maintain the isothermal condition.
So actually everything the same, only the alpha is different, then
Alpha is
the
negative,
property
yeah.
become different. The behavior different because of that.
Yeah, I'm guessing the alpha determines the property lah, because these are all macro state ma. The alpha is micro state. Might say micro state, but like the property of the material lor. I think that's what it's trying to say lor. From this equation. Honestly though.
Yeah, actually.
But it's just math lah, just math it out.
Thanks man.
Then the other one is which one?
Oh no, these two lor.
Oh.
Will he release our result or not?
Huh?
Will he release our result? Oh, is it? He say haven't.
Huh? Then yesterday, was it yesterday? Tuesday he say, yeah, Tuesday right? Monday he say, Monday during lecture he say generally release out well.
Yeah, Harvin, I'm meeting with. You ate already, right?
Oh yeah.
Later I meet you.
He here lah.
My result don't know how careful. He leave me hanging like this.
Which one? I just need question 4 already now.
Huh?
Cause like I managed to get 1, 2 and 3. Just question 4 will follow.
Ask Harvin.
I haven't done yet actually.
I did this at 3:30 this morning.
Wow, siapa activity sia?
Living the life really.
Yeah man.
Shit, I still need to do my report. I haven't finished. I'm gonna die.
You know I slept for 45 minutes on the whole day today.
Why? How you alive sia bro?
No, yesterday I got orchestra practice. Then by the time I reached back my room is 10 o'clock. Then by the time I started work it was 10:30, 11 o'clock. So I cleared email first.
What you do at night?
Huh?
What you did at night?
Orchestra practice.
Oh, you got
Then the whole of
orchestra.
yesterday I did physics. Then there's one graded assignment I forgot to do.
Wow,
Then expires at midnight. Then I completely forgot about it.
What instrument you play? What? What's that?
Radio, explain to Harvin what's the French one.
Oh, French horn. Oh, okay. I know. Oh, means you also, Kevin also got
Kevin also
orchestra.
orchestra. Yeah.
Wow, you guys can play together, sir. You guys all,
Press on? No, this way. Yeah. Oh, this way.
you guys all cool, sir.
Right hand or left hand in bell?
Right hand.
Right hand.
Oh, rabak sia yesterday. Cause like I was today I tried tutorials right?
Today.
Yeah.
Okay.
Then I prepared like 0 tutorials yesterday night. I said yesterday night 10 PM I had prepared 0 tutorials. So I was like okay, I'm gonna start. So
Until what time?
6:30 morning. Then I slept. I fell asleep on my table at 7 o'clock. 7:45 I woke up, then I shower. I got tutorial at 9 o'clock.
Wow, really uni life, sia. You got prepare the tutorial lah? No. Same sia. I also didn't prepare sia.
First time, sir.
Oh, like more than half of my time was freaking 1008 the lamps Wow.
Oh yeah, I also did the lives.
Hey, the lamps, right? What is tested for next week?
Week 3's lamps, dude.
Only week 3, ah?
No, yeah,
only week 3.
Huh, only week 3.
Yeah.
Oh, 3.1 to 3.3.
Can. I already do week 3. Okay, good. What's week 3? Yeah, I need to go already.
Zero code, so
I don't know.
See you later.
Something else I can't remember.
Just memorize, right?
I don't know what lah. Anyway, it's hands on. So,
Yeah.
Oh, but it's first book, right?
First book, multiple choice like your lamps all.
The lamps? Or the...
Like the lamp quiz, I think.
yeah.
Yeah, but that's 50%, eh?
For lamp quiz, I refer to PowerPoint ones. Sometimes I Google.
Oh, for last night's one, right? Because week 6 already, right? They ask you the code, right? Then what does this show, right? I freaking just download the code and then run it. Then see which one's the answer.
Wow, he's legend, yeah. What the hell?
Just use the online GDP or don't know what lah. Use the answer key. This code, no, it's just like realistically, right? Coders, right? What they do most of the time is Google Sheet.
Shit,
Right.
I don't know actually.
So you do lamps already,
I only do last week one because
Fuck, I forgot about that.
I did, okay, so yesterday I did last week's one and this week's one.
missed
And
the.
this week's one is damn heavy.
Is it?
It's damn heavy.
Oh shit! Today actually you attend today one or
Today I never go, cause
today Alvin go until 12 o'clock. Yeah, normally like 11 plus come on.
also it's all the way one, ah.
Yes, yeah. Seems like very a lot content heavy, is it?
So this one is quite heavy, yeah. He said it himself during the tutorial. Today is quite heavy.
What yeah?
Today is
It's a string thing, right? After the string thing, like, I forgot.
string list dictionary.
Wow, that already yeah. Week 5 I a bit struggle already like.
This one's today is really a bit heavy. Yeah. When I saw the the length the slides, right? I saw one of them got 74 slides. Like,
Oh fuck, 74 side. What the shit, bro?
I saw wait, I got show my life. I was like, oh, I'm in for a long night already tonight. Sure enough, until 6:30 in the morning. I woke up at 6:30 yesterday.
Wow, jialat
So
sia.
I 24 hours.
When is recess week? Next week. Oh, 2 more week. Wow, cannot leh. I thought next week then I can just relax all the tutorial for this week.
Then you need to study, like study.
Yeah, I need recess week to study. I cannot catch up sia. This kind of me.
Bilani lah, don't sleep lah.
Cannot lah sia. I'm still human being, bro. I'm not legend, bro.
So I cannot do this to my force.
No money, bro.
Force it. Okay, but how was this week's tutorial? I didn't hear the first 4 questions.
Which one?
The first 4 questions. Is it okay?
Okay lah, not too bad lah. Actually, only this time the tutorial is not that bad.
I don't understand, right?
Only derivation or sub in, sub here.
Yeah, it's just sub in the Maxwell relations.
You can attend the next one.
I know. The next one is my original group. Because my chem tutorial is very short because our questions are just like damn short. And the prof trying to really stretch out the time lah. And he talk very slow, talk very long. Wow, tell a long story. He could go a bit faster, but he doesn't want to go. So like that lah.
Yeah, I saw the comment.
Eventually he still finished early lah. Finish about almost half an hour already. So I time came and crashed.
No, I oversee that. What the fuck? I saw that he said what is this kind of something.
Because like when we finished it was about 1:30ish. Because my camp tutorials will end at 2. Yeah, so 1:30 means you only half an hour.
So you first subscribe.
So I thought myself join your.
You leave lah after question 4, then after that you count.
But
You don't have anything anymore.
I don't depend on sleep. Dude, I got
You got humor or not?
no.
Oh, don't have. Ah.
I got bio.
Yeah lah. Set lah sia bro.
Got bio CA next Tuesday.
Every week you got CA sia. What the hell?
Oh, last year 4 CA.
Wow.
3 CA. Yeah, 3 CA. This week rest. Next week one more.
Username Because I use a username.
Last year was bad man. My physics 101.
What is that?
It's the physics mod lah.
Oh.
Under SPMS one.
So first. Yeah, I go first. Go first, bro. Then I'll see you around.
It's not tomorrow, no. This week tomorrow.
Huh?
This week the lecture tomorrow.
This tutorial.
The Git 3 energy one.
For this ah?
The Monday lecture.
Oh, haven't lah.
I went to look at it this morning. What's that? Gone.
You get it where?
I think Raspberry yeah.
Oh, sorry.
Okay, you.
I was only good every year. Near do like report.
Right.
Here, correct. Oh, bro. One life so